Okay, so thank you for the kind introduction. Thank you for having me here. I'm supposed to talk a little bit about humans can see in 3D and now mobile devices can do. And I'm going to start briefly about what Wikitude is all about. This shouldn't be a sales presentation, so this shouldn't take you longer than 1 minute. So at Wikitude, we're around for quite a while now. So since 2009, we are enabling augmented reality. So like our core focus is really to provide toolkits, to provide a platform that our customers and partners can create exciting AR experiences. We have about 2,000 customers right now who have like commercial licenses, who have published their apps in the app stores, ranging from small developers up to like really large Fortune 500 companies. In total, there are about 500 million applications out there who have Wikitude technology embedded in there. And this is what we do, just like enabling augmented reality and making sure we provide the tools that our customers can access the market as easy as possible. But now back to my title. So humans can see in 3D. So let's make one step back. What does that mean? Humans can see in 3D. So what is the key difference between like a poster and like this kind of Star Wars trooper? So and the main answer to that is depth, what I said earlier. So it's all about depth. And this is exactly the key challenge for the human brain as well as for a computer vision principle. Making the step back and talking about the human brain. How do we humans perceive depth? So when you look at this image over there, it's very clear to us that this is a long street. There are cars, and there are cars that are farther away, and cars that are closer, and there is grass on the side. But of course, this is very natural. But when you think like from a kind of biological perspective, there are certain kind of patterns the human brain is looking at to extract this piece of information. So on one hand, we look at familiar size. So we realize that the car in front is larger than the one in the back, so therefore it has to be closer. So a very clear cue about depth information and distance and perspective. I also mentioned a relative size. When we talk about occlusion, it's clear that even though we only see like part of the car, we know cars so well that it's clear to us what this car is all about. That it's clear that this is like just based on our experience, based on our kind of human patterns, we know what this car is all about. And I think in computer vision, we would call this more or less a machine learning. Another factor up there is like texture gradients. So we realize that the grass in the foreground is like very sharp, has like very clear contrast, is very crisp, whereas in the background it's getting blurry. All these are kind of information in an image we can extract very easily. It sounds very logical for us and logical to us, but when you think about a non-human device, this is super hard to accomplish, to get all these patterns and this information out by a non-human device. So what is the human brain doing there? So on one hand, all these kind of monocular cues I talked about. So the brain interprets these monocular cues and interprets depth information out of that. Like another aspect, the brain can benefit a lot is like that we have two eyes. So we can really perceive the whole scene from two angles with two eyes, and based on that, kind of merge the images and extract the depth information out of that. This is actually a fantastic principle. When you kind of derive from that principle some kind of computer vision logics, this would be like the fantastic computer vision algorithm. However, when you think of like a normal phone, when you think about like a normal wearable device, we have just one camera, just one eye. So all these principles don't really work that well. So what does this mean for a non-human device? So what can we do there to kind of get the same information the human brain does and kind of extract it for non-human purposes? So on one hand, of course, you can work with a stereoscopic camera. It's a very clear principle. You have two cameras, like you have two eyes. You have a very fixed width. You have very clear perspective and can calculate quite easily any type of depth information just derived from these two cameras. Second option is like a depth sensor, mostly based on infrared. The sensor gives you depth information, which makes it a lot easier to kind of record and track and recognize things in 3D. The third principle, this is our philosophy, is really working with smart computer vision algorithms. So, of course, it's great if we have like helpers from the guys at Intel and in Occipital to kind of give us sensors and make it easier for us to kind of get 3D information from the real world. Still, the mass market have like those type of devices. They have a single camera. They don't have these sensors, and therefore we focus our research to get the best results out of these kind of mono cameras. So of course, if we have more information from those kind of step sensor cameras, it's perfect. We can recognize and track things easier, but still, the research goal has to be to get the same performance from a single mono camera. When we talk about computer vision, what are like the things we are looking at? And please apologize if this is too basic for some of you. So I talked about the human brain, I talked about the human eye. When I'm a camera, when I'm like a processor and a computer vision algorithm, I look at different aspects in an image. I look at like edges. Edges help me a lot. I look at like corners. Corners are really important to kind of track the scene and get information from this scene. I look at feature points. Feature points is really important to kind of get the texture and the characteristics of certain objects in real life, in real world. If edges are kind of too drastic, you work with edgelets, which are just like pieces of edges and help us a lot to kind of recognize scenes in real world. And last but not least, typically every phone, every variable, every glass has like sensors in there. And the combination of like vision algorithms, vision cues, as you see over there, combined with like motion information derived from those sensors, that's a very strong combination to really make a non-human device see in 3D. I'm going to show you 2-3 videos to give you a better impression what are the kind of challenges in kind of recognizing 3D content. So what you see here is like recognition of an object. Here, like the principle we use are like feature points. So this means this object is like has like very clear features. It has like it's structured. So therefore the algorithm has to focus on these kind of features and use those to recognize that object, track the object, and keep the augmentation on top of the object. When you lose it, it's going to be reinitialized. So again, the principle that we use here is like feature points. When you look at that video to the bottom right, this is a different type of object, you see. So it has like less structure. It has, it looks different the way it's being positioned. You can't really work with feature points. So you have to work with silhouettes, with edges. This is what is like called edge tracking. And this is like another type of computer vision principle to work with certain objects that have a smaller number of features. This is relevant for recognizing a car by car silhouette. This is relevant for things like engine parts that are kind of glary, stuff like that. So as mentioned, these are kind of algorithms and approaches relevant for object type recognition. When you want to see 3D outdoor, it's totally different. You can't work with feature points. You have like different weather conditions. You have like different raining. You have rain and lighting conditions. So this means you need to have different algorithms and approaches. In this example, we just like use a church in our hometown in Salzburg. Recognize the building structures, try to be as robust as possible versus against like changing lighting and environmental conditions, and kind of place like this kind of steeple on top of the church that used to be there before World War II. So again, 3D recognition, but a totally different problem to solve in computer vision. And last but not least, 3D also means motion. So this means when you want to kind of move in a room for like mixed reality use cases, when I want to use 3D recognition for like indoor navigation, then motion is a very important factor. So this means the key thing here is combining computer vision with sensor fusion. And what you see here in this video, so our colleague here kind of moving the phone. On the bottom right frame, you see how the computer vision algorithms kind of recognize the scene. On the left window, you see the kind of track of the phone. And this is a very smart combination of utilizing sensor information and computer vision information. So again, 3D, but still requiring different type of algorithms. So to kind of conclude this presentation roughly. So 3D, that's a huge challenge. So it's something that's being researched for a lot. And right now, there are good point solutions for for multiple projects and multiple challenges. However, the key goal has to be to have like one single platform that solves all these problems in a ubiquitous way. So like as a kind of developer who kind of writes augmented reality applications, you shouldn't have to worry, shall I use an edge detection algorithm, or shall I use kind of point cloud algorithms, or shall I turn on the IMU? So the key challenge here has to be to have one AR platform that chooses the right set of technologies for the right challenges in real world life. And yeah, this is pretty much our key vision. So starting with point solutions and kind of merging them into kind of an ubiquitous 3D AR platform that allows us to kind of recognize and augment the world in a full 3D environment. Thank you very much.